Hello, this is going to be our 8D. This is going to be talking about the dynamic theory of tides, or just basically what we really see. If you remember, we talked about the other type, which was actually talking about the physics behind water, physics behind the seafloor, physics behind meteorology, what actually should give us our tides, but this is the dynamic theory, how we really get them. So first thing we got to figure out is tides are shallow water waves, and what this basically means is their speed varies with depth, and we'll talk more about this in Unit 9 when we actually talk about waves. There are shallow water waves, there are deep water waves, and there are what are called intermediate waves. This is a shallow water wave, which basically means that the wave is actually touching the bottom of the ocean no matter what the depth are, because these are 6,000 miles apart. They can reach down 3,000 miles, and we don't have an ocean that's that deep. So shallow water waves, and they are dependent on depth. They lag behind the Earth's rotation, which basically means the Earth is rotating in this direction, and the tides are a little bit behind it because the moon can't keep up with it, and the rotation of the Earth is spewing that water a little forward of where it's supposed to go, and what that does, it slows down the rotation of the Earth. It also allows the moon to move farther away. We do have a rotary flow in an open basin. We have what are called amphidromic points. Those are these red dots that you see, and the water actually tends to spin around them. The points are called cotidal, or cotidal is I think the real pronunciation, but cotidal actually makes more sense. It actually brings in the tides and makes them together. So the points, amphidromic points, and the lines that you see with the different colors are cotidal points, and they're actually showing you hours worth of tide motion. So here they are, a little larger view. Here's the North Pacific, there's the South Pacific, there's the North Atlantic and the South Atlantic, and you can see that they actually move this direction. They start with 0, and they're there an hour later. They're there 2 hours later. They're there, 2 hours later, 3 hours, 4 hours, 5, 6, 7, 8, 9, 10, 11, and 12. And then they start it again for the next tide that comes through. And this is one of the reasons why we actually have all these points. I just had one of my cats come into the room, and I was wondering why they're coming in. So the crests of these actually make the high tides. As they rotate around, they go counterclockwise in the northern hemisphere, as you can see, and south of the equator, which is about right there, they go clockwise. So they're moving clockwise down here, and they're moving counterclockwise up here. And you can actually see that there are more of these rotary motions in the southern hemisphere, because remember, that's the ocean hemisphere, than there are here in the northern hemisphere. They don't really go up here because it's ice. They do, because this is that mercantile map, it actually pulls this section apart, and you can see that that flow does move into this section going around Iceland and some of the other islands that you see up here. Tide patterns are diurnal. We did a web assignment on these already, and we did a lab on it. Diurnal meaning that we get one high tide and one low tide per lunar day. So there's 0, there's 24, there's our one high tide, and there's our one low tide. One high tide and one low tide each day. Period of these are 24 hours and 50 minutes. Remember, the moon is actually moving around the Earth, and it takes 50 minutes for us to catch up to that motion every day. So it's our spin plus 50 minutes. Semi-diurnal, we get 2 high tides and 2 low tides every day. So you can see there's the 0, that's the 2 days, there are 2 highs, there are the 2 lows. Tidal period is the high to low, and tidal day is the 24-50 minutes. And you can see not just 12 to 12, it's a little bit more. Period is 12 hours and 25 minutes, because 2 of those are 24 and 50. And they have equal range. Then we have what are called mixed tides. These are 2 high tides and 2 lows each day, but they actually are different ranges. So we actually see that the tidal period there, and a tidal period there, and we have a tidal day there, and we have higher low tide, and we have lower low tide, and we have higher high tide, and we have lower high tide. And because they don't have equal range, they're called mixed. Mixed tides are the most prominent tide on the planet. You can see all these green, excuse me, that's not green, that's blue, almost purple. You can see all the purple lines that you see there, they're mixed. semi-diurnal tides, 2 highs and 2 lows in all the reds, and the yellow areas are actually experiencing 1 high tide and 1 low tide diurnal. Here's the one from the Chesapeake Bay, and remember, this is what we actually expect the tides to be, this blue line, and the red dots you see are points in time that we actually do experience, and this can actually be caused by storms and other things, and that's probably what this one was, because it's going to be so different. Standing waves. Standing waves are waves that actually don't seem to really move. They're like this black line that you see right here. They just slosh back and forth. And they're forced waves caused by tides. They are freestanding waves when they're caused by seismic disturbances. And they're called seiches if they're actually in a closed body of water like a lake. We saw freestanding, if you've seen the movie San Andreas, and I tried to find a YouTube video of it. I should record it off the screen next time it plays. But freestanding waves caused by seismic disturbances. San Andreas was supposed to be a big earthquake. I think they said it was a 9.6 in San Francisco, 9.3 in Los Angeles area. But the seismic disturbance, but it also caused a seiche because that was an enclosed pool up on the deck. Right at the beginning of the movie, the Los Angeles earthquake, when the wife was actually up in the restaurant, saved by the helicopter with whatever his name is, The Rock. I forgot what his name is. Kids have told me that last week too. But anyway, he saved her from while he was in a helicopter. But right as she gets up to the top, she watches this pool slosh back and forth. That would be a seiche caused by a freestanding wave in a enclosed body. So we do have what are called the nodes. The nodes don't really move. That would be in the center of this thing. And then we have what are called the antinodes that go up and down. We do have, when we talk about waves, you'll see the same thing. When you see the crest of one get to the trough of another, you see it's a flat body. But those are the nodes right there, and these are the internodes caused by these moving bodies of water, internal waves. Same sort of thing, we have what are called destructive and constructive, and that's when the two crests come together for constructive, and when the crest and the trough of two waves come together to make a flat body, that would be the destructive wave. Same thing on this red one. You see it move up when the crest and the trough are there, and it hits this normal wave. So we get a maximum flow right at the node. So as the node actually moves back and forth, you see those things go horizontally back and forth. And then we get in the internode period, this section, we get the very large vertical flow of water. So this water goes up and down, and this kind of slides back and forth. So we get horizontal flow at the node, we get vertical flow at the antinode. Bay of Fundy, I'm not going to click these links now. I will show them to you in class. I found if I click a link, I get a copyright warning on my videos, so I'm not going to do that. Bay of Fundy is actually located right up in here, and basically what happens is we get a very large tidal range that's actually 17 meters. Multiply that by 3.3 and you get a really large tidal, high tide, low tide difference. And it's caused by the shape of the basin. It's caused by the oscillation period that's close to this tidal area. It's caused by the shores narrowing to the north, and it's actually caused by the fact that the Coriolis effect helps throw the water in there. But this is the Bay of Fundy during high tide. This is the Bay of Fundy under low tide, and you can see that this ship has to pay attention to when it wants to come in and out, because sometimes it cannot move. Also means you have to have a different design hull. Most hulls are not actually made to support the weight of the ship, because the water usually does that. So ships have to have their timing very well, and they also have to be built a little different. We also have what are called tidal bore. Tidal bore is called when you get that same section for like the Bay of Fundy, and where you get this incoming tide, which is called the flood tide. And the crest of that tide can make a wave. And I've actually been in a boat up in the Bay of Fundy where you actually ride the boat. You ride the boat right in front of this crest, and it just pushes you up the stream. So this is caused by tidal rushing upstream. It's caused by large tidal range. It's caused by low-lying coastal river. It's a very steady sloped river. Maximum 8 feet of height. And I'll also show you this movie. So I'll probably show you one of Bay of Fundy, and I'll show you this one. This one is of a competition, a surfing competition in China on the Silver Dragon River on their tidal bore. And I think the last thing we have to talk about is power of tides. What we can do is we can actually put these propeller, like almost like, I don't know, propeller like windmills underwater, and you can see it's got a fin on it, so it actually moves back and forth compared to the tide. And if the water flows, it propels this, and if it actually does that, it can produce electricity, and then we can put that into wires underground, and we can send that up. Or we can actually put dams across sections of the tide. We can let water move into it, opening up this one, we close this one, we let water flood tide move in, and then once the high tide is there, we close this main valve and we open this one, and as the ebb tide goes back out, it actually turns this turbine, which will actually move a magnet inside of a copper wire, which is how we make electricity, same thing that's going on in here. So if we can get something to spin and actually make that magnet spin in that copper wire, we can make free electrons, and we can collect those electrons and send them out for usage. So that is the end of the section. Remember, it's all caused by gravity pulling water out, centripetal force pushing water in towards the center, and the net force pulling water that direction. This one, they're equal, so there is no water, and that's where we get the low tide. And here we get more centripetal center forming, and these are all pointing towards the sun. These are all pointing toward the moon, and we'll actually, when we can get those things to flow in the same direction, then we can, like when we get the moon on this side of us, we can actually get this gravitational helping with this centripetal. We still have gravity pulling the water in, but we can get bulges on both sides. And these are the high tides, and the low tide would be this side, and the other side of the Earth on the other side. Okay, that's it for Unit 8. Thanks for stopping by.